Welcome. Everybody knows that bodies can deform. Deformation, however, can happen under very different conditions and produce very different results. Materials have obviously different strengths, which means that a larger force will be needed to deform a strong body, whereas a smaller one will be enough to deform a softer one. The same material, on the other side, can deform in different manners. The candy bar you see in the picture, for instance, can be broken in two or can be deformed in a continuous manner, changing shape but without losing continuity. In this model of our MOOC, we will focus on when and how rocks break. We will first enter the rock mechanics laboratory, analyzing how rocks deform in a controlled environment, and we will then look at how they deform in nature. The machine you see in the picture is a rock deformation press, similar to the one we have in Delft. The apparatus consists of two pistons which move towards each other, squeezing the rock, and an electric resistance to perform experiments at different temperatures. A confining pressure can be applied around the sample to replicate conditions at different depths in the earth. When the experiment starts, the piston squeezes the sample, shortening it in the vertical direction. Once the experiment is finished, you open the machine, extract the sample, and analyze what the sample looks like. Depending on temperatures, rock can deform in two different ways, defined as the low temperature and the high temperature regime. We first look at the low temperature regime. A common way to display the results of rock mechanic experiments is a stress-strain diagram. On the horizontal axis, you can see the strain, which is the shortening experienced by the sample during the experiment. On the vertical axis, you have delta sigma, which is the difference between the stress applied to the piston and the confining pressure, which was decided at the beginning of the experiment. Note the vertical stress applied is the one needed to keep the formation going at a constant strain rate. In the initial stages of the experiment, you can see a linear relationship between applied stress and strain. This means that deformation can only occur if the stress keeps increasing. If you would stop the experiment here, no further deformation would occur. If you would remove completely the stress, the sample would go back to its original shape and size. We call this the elastic domain. Stress-strain relationships are described by Hooke's law, which states the strain is a linear function of the applied stress. If you continue the experiment, the rock will break. The stress will drop and the experiment will end. Apply a high confining pressure, the experiment continues, and the sample passes the yield point, which forms the boundary of the elastic domain. After the yield point, the stress strain can have different shapes. It can keep on climbing, it can flatten, or it can even descend. The latter case implies that less stress is needed to keep on deforming the sample at the same strain rate. The sample has become softer. You can also see that the experiment continues much further than in the previous slide, and that therefore a lot of deformation can be accommodated. Open the apparatus and cut in the rock, we can see what happens in the various stages of deformation. In the first part of the curve, the sample develops a large number of small fractures spread over the entire rock. With proceeding deformation, old fractures become longer and new fractures will develop. Under low and intermediate confining pressures, fracture concentrate in specific part of the sample, eventually leading to the development of a through-going fault. This marks the end of the experiment. Faults typically come in pairs, the acute angle being 60 degrees and being cut by the direction of maximum compression. At high confining pressure, fracture will be distributed throughout the entire sample. No through-going fault is developed, and the sample will deform, acquiring a barrel shape. Stress-strain curves in the high-temperature domain look substantially different. The first diagram shows the formation curves obtained in experiments with different temperatures. Clearly, the rock becomes softer at higher temperatures. On top of this, it can accommodate much more deformation than the colder counterpart. The second plot shows the formation curves with different strain rates. Note that because of the negative exponent, curves in the upper part of the diagram correspond to faster experiments than those in the lower part. The message is clear. The faster you want to deform, the higher the stresses you need to apply. On the other side, if you have a lot of patients and time, you will need very little stresses to achieve large deformation. A third important factor not shown in this diagram is that stress-strain curves for different rocks are very different from each other. From the plots, you can see also that the samples in the high temperature regime can accommodate large deformation, and they do this without losing continuity. Rocks deformed at high temperatures look very different from their lower temperature counterparts. Even when they are highly deformed, they will not break, and the deformations are accommodated by changes in the shape and dimension and structure of the crystals. The sample always preserves the continuity. Rocks that deformed at high temperatures are often called mylonites. Here is a summary of the most important things we have learned from the experiments. We can distinguish two different regimes, namely the low temperature regime and the high temperature regime. At low temperatures, samples start deforming in an elastic manner, developing many small fractures spread in the body. At a given moment, there will be so many fractures developing in preferred zones of the rock that they will break and forming a large-scale fracture. This fracture can be parallel to the axis of the compression or oblique to it. At higher temperatures, the behavior is very different, and the amount of stress you need to apply is directly proportional to the rate at which you want the deformation to occur and inversely proportional to the temperature at which you work. Different minerals have different strengths. In general, samples do not break and can absorb as much deformation as made possible by experimental apparatus.